Topic 3.2 Concept of stress and strain. If you look at this piece of metal, it is cylindrical shaped with the dimension of L0 along the length and the A0 along the cross-sectional area. Along the vertical direction here, under tension, this piece of metal has been extended along the length, and here we have the reduced cross-sectional area with increasing length, as you can see from this picture. And here we can calculate the engineering stress, which equals load divided by original area, which is the A0. And hence we have S for stress equals P over A0. As the convention for tensile force, the values is always positive, so we have the positive values of the tensile stress. On the other hand, if we started from the same cylindrical rod-shaped metal with the original dimensions of L0 and A0, but this time we apply compression load onto the sample, and here the length has been reduced into this dimension, but on the other hand, the final area is increasing. And so in this case, we also apply the same concept of stress, which is the engineering stress equals load divided by original area. But this time, the load is in negative values because it is compressive. So in compressive, remember, is the negative values of the stress. But then if we talk about the concept of strain, the engineering strain equals change in length divided by original length, or you can see as in the formula here, E equals L minus L0 divided by L0, or delta L divided by L0. And again, this concept can be applied for both under tension and under compression. But remember, the strain under tension is positive because the dimension has been extended. We have increasing amount of length. But for compressive, the length is reduced. That's why engineering strain is negative under compression. So remember, under tension, we have positive values of tensile stress and strain. But under compression, we then have negative values of compressive stress and strain under the same concept of engineering stress equals load divided by original area, and engineering strain equals change in length divided by original length. So before we go further, let's have a look at the unit of stress and strain. For stress is load divided by area. The unit of stress is Newton divided by meter square, or we can call it Pascal. And for strain, you can see that strain is dimensionless. And if you look at this slide, you can see that there are examples of flow curves of various metals. So you might want to know what the flow curve is. The flow curve is a graphical demonstration of stress and strain. The strain is plotted along the x-axis, while the stress is plotted along the y-axis. And here we have different sizes and shapes of flow curve, which I will tell you a little bit more how different materials behave differently under tensile loading. And you can see that this flow curve is plotted on the positive axis of the stress and strain. And this means the result here obtained from the tensile test, not the compressive test. And therefore, these are the tensile stress and tensile strain. First, I introduced you this red curve of the structural steel or mild steel. And you can see that the structural steel doesn't give high stress, but huge amount of strain over here in comparison to other graphs. It means that this structural steel is deformable and can change its shape to various types, and it is good for construction as well. But then, when we compare with another one up here, is another type of steel that has been quenched and tempered. Is another type of steel with a different composition, and this will come with higher carbon content and other alloying elements. And this type of steel can be heat treated, for example, quench and temper to give much higher strength but a little bit lower ductility or lower strain. And you can see that even they are classified as steels, but with different composition and heat treatment, it can give so much difference between the two types of steel. And you can see that the area under the flow curve signifies the toughness parameter, and toughness can be defined as the strength plus ductility that is comparative to the area under the flow curve here. And if you compare the areas under the flow curve of the structural steel and the other one above here, you can see that huge amount of area under the steel that has been quenched. And to this means that this type of steel can be used at much higher strength level, but still remain some of the ductility here to provide safety factor for this type of steel. Now, let's have a look on other type of metals. These first two are considered as ferrous metals because it's based on iron that is alloyed with carbon. Here are another group of ferrous metal. Stainless steel differs from steel by adding chromium and nickel to make different microstructures. But here you still have high strength in both types, a little bit different strain. But both make these two stainless steel different from the previous steels. They can offer corrosion resistance, which is much superior than the normal steel. Now, let's move on to a non-ferrous alloy. Here you see the green curves showing the stress strain or the flow curves of their aluminum alloy sheet. Right, for this type of non-ferrous metal, you can see that the flow curve is much smaller in comparison to the steel and the stainless steel. And therefore, aluminum alloy is used for structural materials that cannot bear the very high load. As you can see, we use for windows and doors frames in construction applications. That's for example. And here is another type of non-ferrous metal, titanium alloy. And therefore you can see titanium is much tougher than aluminum. And another one here, nickel alloy. And nickel alloy has a very good strength and can be used at high temperature because of its high strength over here. These are some examples that I can give you and shows you that different composition and different treatment that have been applied onto the metal alloys itself can change the flow properties of the metals. And this will influence how the metal will be applied for different engineering applications. And this is the concept of stress and strain for metallic materials.